Okay, very warm and gracious morning, respected dignitaries and dear participants. Myself, Mintu Ghosh, HUD of Mechanical Engineering Department, Bengal College of Engineering and Technology, Durgapur, and also the coordinator of this short-term training program as well as faculty development program, extend my heartfelt greetings to one and all present here on this online platform. A hearty welcome to the fourth day first session of this 5 days program on recent advances in intelligent systems and smart technologies for core engineering applications from 10th March to 14th March 2026, organized by the Departments of Core Engineering and Basic Sciences of BCET Durgapur in collaboration with the Institution of Engineers India Durgapur Local Center. I feel proud to welcome our ex-student Hemant Kumar Mandal, 2007 pass out batch from Electronics Department of BCET and who is now well known as Dr. Hemant Kumar Mandal as a distinguished resource person for this fourth day first session on the future of the VLSI industry, growth and career options. Dr. Hemant Kumar Mandal is an assistant professor in the Department of Electronics and Communication Engineering of National Institute of Technology, Durgapur. And prior to this, he worked as an assistant professor in the Department of Electronics and Communication Engineering of Indian Institute of Information Technology, Guwahati. He was also associated with the National Center of Scientific Research, Lab STICC, UBS University in France as a postdoctoral researcher. He received his PhD from Indraprastha Institute of Information Technology, Delhi in 2017. He also worked as an intern as Freescale Semiconductor Private Limited, India, and as a visiting researcher at STM Microelectronics, India. His work has been recognized at multiple venues in the form of a student travel grant for SOCC 2014, student travel grant for attending VLSID 2017 and VDAT 2016, PhD forum presentation at VDAT 2016, VLSID 2017, and DATE 2017, research showcase as IIT Delhi, research seminar at CNRS Lab STICC, catch-up talk at IIT Delhi, and he has been able to publish in premier venues such as IEEE TMSCS, IEEE TSUST, ACM JETC, Journal of Supercomputing, SF Computing Springer, Elsevier, etc. He was chairperson of IEEE student branch of IIT Delhi from July 2014 to August 2016. He also presented the tutorials at VLSID 2017 and VDAT 2016 conferences. Apart from that, he has 57 international publications and 3 consult projects. Now, I would like to hand over this session to Dr. Mandal, and I am sure we all will be enriched with the knowledge and enjoy the learning. Now, the session is over to you, Dr. Mandal. Please take it in your way.
Okay, so am I audible to you?
Yes, you are audible, fine.
Okay, so thank you, sir, for it's a long introduction about me, and it's a great privilege to be here today. And now, so let me share my slide first. Okay, just a minute. I think it's visible, right?
It is visible, plus you can make it full screen.
Yes, I'm doing it.
Yeah, now it is okay.
That's clear, right? So today, as a part of this FTP program, I'm going to tell you on important topic nowadays, that is VLSI design. So this is one of the hottest topic or hottest area where we can invest more time to get more opportunity. So today I'm going to talk about, or my title of this talk is the future of VLSI industry, growth and career options. So maybe today I'm not going to detail about the VLSI technology or detail comprehensive journey through the critical steps of chip design. For that we need another sessions. Okay, so today I just want to motivate you towards VLSI design and why VLSI design is required and nowadays, and why it is one of the most hottest topic in present day context. I'll explain this thing in detail. Okay. So now before every session or at the beginning of every session, I generally mention this to nice quotation. What's wrong with India's engineers? So as many as 97% of engineers, basically 97% of graduating engineers want jobs either in software or core engineering. But only 3% have suitable skills to be employed in the software or product market. And only 7% can handle core engineering tasks. Another one, graduates are collecting their degrees despite not being skilled enough to be a productive part of the Indian economy. So what I mean to say, so life after BTech or whatever, or graduation is very, very competitive or challenging. So to survive, we need only one thing is required, that is skill set. Otherwise, it is very difficult to survive, because every year almost close to 20 lakhs engineers they are getting their degrees. Now think about it's not about government sector, or it's not about government college or private college. It is equally applicable for every colleges. So it's an alarming situation nowadays that there is a big question about survival. You may get job easily in the software domain or hardware or VLSI domain, but you have to fight for the existence. So this is one thing I would like to highlight over here. So now let's talk about need of VLSI chips as a part of motivation towards VLSI industry. So first of all, VLSI chip is required almost everywhere, wherever automation is required. So application like scientific applications, astrophysics, weather prediction, then consumer electronics, cloud computing, multimedia applications, embedded systems, exascale computing, defense, security, medical, IoT, AI, data center, neuromorphic computing. Almost everywhere VLSI chip is required. So these two, as you can see, these two figures are from one from Facebook data center, another one is from Google data center. Now why I'm showing it over here? Because whether you are surfing basically Facebook, WhatsApp, or any other social activities, okay, through social media. For each and every activity, huge amount of data will generate. Now we need to store those data where in data center. Now for data center, we need a huge amount of VLSI chips. So apart from this, as a part of Indian semiconductor mission, requires more than 60,000 highly skilled manpower in the domain of VLSI. So there is an immediate requirement. There's an immediate requirement we need in India. Already a lot of fab labs they have already set up in different places across the India, like Gujarat, Assam, and Andhra, as well as UP, Greater Noida. So they need immediate 60,000 approximate skilled, highly skilled manpower in the domain of VLSI. Because there's in the present day there's a shortage of chips, because high-end automobile, high-end cars are available nowadays. EV sectors or everywhere, automobile section, defense sections, everywhere we need VLSI chips. So now next, move to next slide. That is India's VLSI industry on the right track for growth. Is it so? Answer is yes. Now in December 2021, India announced its roughly $10 billion scheme. India would increase to 70 to 80 billion by 2026. The growing demand for digital devices and electronic products. India and US have separately initiated policy decision to build manufacturing capacity. Already they have started in India. India's shares of global electronic manufacturing will rise to about 10% in 4 to 5 years from the current 3 to 5%. Worldwide semiconductor industry is currently valued at $500 to $600 billion. Global electronics industry currently valued at around about $3 trillion. So a lot of facilities are basically a lot of companies they are already invested in they are investing, and a couple of companies they are planned to come up in the next soon in India. Tata Electronics has announced a factory. Already they have set up in Gujarat and Assam. Osted Plant, Micron, CG Power, Renesas, Star Microelectronics. A lot of companies they have already started or they have already because one thing was missing in India, VLSI, if we divide into two broad categories, one is basically design part, another one is manufacture part. Design part we are basically very strong because a lot of VLSI engineers are available in India nowadays, but we are lacking behind basically fabrication or manufacturing half part. Now this part is already we have overcome. Now we need skilled manpower for fabrication or manufacturing plant as well as design sector. So more than you just imagine, more than 100 billion semiconductors are in use every day. More than 100 billion semiconductors. And if you look at India's VLSI sector is basically booming, driven by projected 100 to 110 billion market by 2030. It's a massive surge in 2026, job opportunities, strategic partnerships. So a lot of things are taking part simultaneously in the domain of VLSI or semiconductor industry. Only thing, we have to motivate our student. We have to provide right resources. We have to instruct them. We have to train them. Then only our student will get this opportunity. Otherwise not. If you only know the VLSI term, that is not enough. But to learn VLSI, it's a very interesting and challenging domain also. If you want to learn, you can learn it. So there's a lot of scope in the domain of or in case of VLSI or semiconductor industry. Now, where are the semiconductors used basically? As a part of applications. Industry, approximately 10%, like automation, healthcare, security. Consumer electronics, 8.5%, like consumer electronic components for personal use, including TVs, digital set-top box, and gaming, and so on. Personal computer, approximate, it is around 22%. Automobile, 8.5%. Communication sector, it is around 35%. So communication is dominated by smartphones. In year 2021, 556 million 5G smartphones were produced. Now you just imagine the volume of the products. Server and data storage, 16%. And for everything, we know Intel, Snapdragon, or Apple product and AMD product. Okay, at the back end, TSMC, they are basically producing their chips for them. Design part they are doing standalone, and they have a collaboration with TSMC, Global Foundry, or UMC, or some other vendors or fab labs for final tape out or design. So there are a lot of almost as I mentioned earlier, almost everywhere VLSI chip is required. Now we have to learn how to design a VLSI how to design a VLSI chip, and what are the skill set are required. That I'll discuss with you in a short while. Now, phases of semiconductor production. Typically, there are three phases. Phase 1, design phase. Phase 2, wafer fab manufacturing phase. Phase 3, packaging, assembly, and final test. Now in this phase, in these three phases, so you can walk in this design phase. You can work in a wafer fab manufacture phase. You can work in a packaging, assembly, and final test phase. So design phase basically we need more time for the design phase. There are a couple of steps are available because you might have three types of design: either analog design, analog VLSI design, digital VLSI design, and mixed signal VLSI design. Now, based on your interest, you can move forward for analog design if you are expert in analog electronics. If you are expert in comfortable with digital electronics, you can go forward for digital VLSI design. And if you are expert in both analog as well as digital, you can go forward for mixed signal IC design. So you must have proper plan before your final tape out, and it takes up to 26 weeks to manufacture and package a semiconductor chip. Now next is semiconductor fab lab. Okay, so design phase I'll talk about it in a short while. What about the design phase? Now let's talk about wafer fab manufacturing of fab lab facility or fab lab requirements. Initially, it's required around $20 billion. It takes a year to build a semiconductor fab lab. So that's why in the year 2021, Government of India, they have announced a lot of companies, they are going to establish their fab lab in India. Now Tata Electronics, Micron, and Star Electronics, they have already produced, tape out a commercial chips, and we are basically earlier what we do, we used to do design over in India, and we usually send our design to basically Taiwan or some other countries. Now we design as well as manufacture, both things are happening in India. it's a quite fortunate and maybe it's a good thing for next generation engineers. Lots of opportunities are waiting for them. We have to maintain the yield. Yield means in the form of good chip and total number of chip you have considered in a single wafer. This ratio is called basically yield. Yield close to 100% means your number of chips is less faulty. Maybe you heard about it. TSMC they have already started work on 1 nanometer technology node, and they are about to launch their product based on 1 nanometer technology node by the end of this year. And a couple of things like we have to invest. So main point is we have to invest a lot of money, $1 trillion for the fabrication lab. So to maintain certain thing, clean room and so on. So initial investment is huge. Now another investment you have to do whenever you move from one technology node to another technology node. Suppose you have designed your chip. Earlier chip was based on 5 nanometer or 7 nanometer. If you check your smartphone spec, whatever smartphone you have, like Qualcomm Snapdragon processor, or maybe Samsung Exynos, or maybe Apple A1 or A2 or A4 or whatever. So you see the spec. So today's chip is based, commercial chips are based on 5 nanometer or 7 nanometer, so on. So next generation chip will be based on, like upcoming chip, 1 nanometer. Now these 1 nanometer, 5 nanometer, 7 nanometer, these are all marketing terms. Although this technology node defines the size of your transistors, a dimension of your transistors or device. So if you are going, if technology node is getting shrink day by day, that means transistor size or dimension will be reduced. Then within the same die area, you can accommodate more number of transistors or devices or component within the same chip area or die area. So you can add more number of features. You just think about 10 years back, your mobile phone features and today's your mobile phone features. Although most of them features are when they underutilized. So another is basically there are 3 different types of semiconductor industry. One is fabless, means design part will do, like Qualcomm. They only do design part. And rest of the part they do outsource from maybe TSMC, Global Foundry, some other fab lab. So the AMD, NVIDIA, Qualcomm, Broadcom, they don't have own fab facility. So they do outsource from different vendors. Only what they do, they design and sell the semiconductors. Another type of company, integrated device manufacturer. In short, it is called IDM. Like Intel, Samsung, Micron, TI. These are basically IDM type of company. They do design, manufacture, and sell semiconductor. Both. And some pure play foundry, like manufacture semiconductor for other company, like TSMC, SMIC, UMC, Global Foundry, and so on. So there are 3 types of semiconductor industry. So you can work in this type of industry anywhere. Now in India, all kind of opportunity you have. Earlier, we don't have this kind of opportunity like pure play foundry. Now foundry options are available nowadays in India. So lot of opportunity. So based on your potential, what you have to do, you have to select your path. Exactly, you want to keep yourself which phase, design phase, or under design phase. Also, there are 2 types of verticals. One is front end, second one is back end. Then another phase is basically manufacturing or process technology based phase. Another phase one is basically packaging and assembly and final test. So worldwide semiconductor revenue reached around 611.35 billion in the year 2023. So this is all about semiconductor industry. There are three different types. At the back end, because lot of equipments, materials are required for fab lab. So at the back end, a lot of company like Applied Materials, ASML, then Tokyo Electron, then Lam Research, KLA, lot of company they are working for basically as a supplier in case of fab lab. You can work in Applied Materials also. You can do a lot of research with the different types of materials. You can do characterization. It's not about VLSI, it's not about only applicable for electronic students. It is applicable for, in case of VLSI industry, it's required, it's a kind of interdisciplinary domain. We need software engineers, we need engineers from electrical department, we need engineers from electronics department, biotechnology, chemical, mechanical, civil, every kind of engineers we need. It's not about, it is not restricted only for electronics. So apart from these different types of industry, you might have, you may join in this type of industry also. Because this industry developed a product to support the fab lab. They developed equipment for fab lab. Because what we generally do, okay, I'll come to next in a short while. Okay, so these are the different industry like Applied Materials, SML, again I repeating, then Tokyo Electron, Lam Research, KLA, lot of opportunity. Their starting salary is also decent, more than 50 lakhs. You think about. And most of the, one thing I would suggest that VLSI industry, most of the cases, they preferred MTech students. What you do during your BTech, appear for GATE exam and enroll in MTech in VLSI program anywhere in India. You do first year, during the first year, like 2 semesters, 3 months each semester. You complete your coursework, and next semester, second year onwards, you go into the industry for an internship, and through internship they recruit generally almost more than 90%, 95% manpower they recruit through the intern. During internship, perform well, and accordingly they generally recruit. And package is nowadays in starting package is more than 50 lakhs. Think about. So next one is career options, career growth. Okay. So now what are the skill set are required to become a VLSI engineers? So first one is basically basic knowledge of CMOS VLSI design. This is required, mandatory. As I mentioned that VLSI, you may break into 3 different verticals like digital IC design or digital VLSI design, analog IC design or analog VLSI design, and mixed signal IC design or mixed signal VLSI design. Now, if you are looking for this domain, digital IC domain, so you must have knowledge of digital electronics. Now, if you are looking for analog IC design domain, you must have knowledge of basically analog electronics. Now, if you are looking for mixed signal IC design domain, you must have knowledge of both analog as well as digital. computer, apart from this, you must have idea about computer architecture. Otherwise, whole things will be looks like a black box. You spend some time to learn computer architecture if it is not included in your academic curriculum. So we know C, C++ or Java.NET. Generally, these languages are basically required to develop a software product. Now for hardware product or VLSI chip, there are two different languages, that is VHDL or Verilog and Verilog. So you can learn VHDL or Verilog. So most of the industry, they prefer Verilog because Verilog is user-friendly language. And these languages are called basically hardware description language. Hardware, HDL stands for hardware description language. Apart from this, basically for testing and verification purpose, you have to learn UVM and system Verilog. I don't know whether you know or not, in case of VLSI domain or semiconductor industry, there is equally requirement of basically software engineers. It's not about only for hardware engineers, because now today's trend is hardware software co-design. Some part, if industry feels, if we go for hardware level implementation, they fix it for hardware. And if they feel that if you go for software level implementation, you will get more benefits, then they are going for software level implementation. So this type of strategy is called hardware software co-design. So for that, we need both types of engineers, hardware engineers as well as software engineers. So there is an equal opportunity. Instead of, if you really wish to go into, if you don't want to change your mind because already you have planned for, I will go for software industry, then software, so join in a software job in case of VLSI industry. Normally typical salary in case of software, average salary 10 to 15 lakhs or close to 20 lakhs. But if you join as a software developer, in case of semiconductor industry, your salary would be more than 50 lakhs. Now in case of suppose you have designed your logic, whatever, logic basic gates, multiplexers, a counter, or finite state machine, milli mode, whatever. Now suppose you have developed this thing and you have validated this thing with the help of simulator. Means you have performed simulation. Simulation means if you do simulation, some waveforms will be generated. Now you can observe that, okay, whether we are getting outcome or whatever outcome we are getting, it is correct response or not. Or you can check your functionality through the waveforms. Whether in case of AND gate, suppose if both inputs are 1, 1 and output would be 1, and if you are getting 0, that means whatever you have designed with the help of Verilog language, that means this is not correct. Means functionality is not correct. Your logic, whatever logic you have defined inside your module, that logic is incorrect. So that needs to be verified through the one process is there, that is called functional verification. So this part you can do with the help of software. Different types of softwares are there, like softwares from Cadence, Synopsys, Siemens EDA, Xilinx AMD. So these are different vendors' name, and they provide EDA tools for VLSI chip design. Now EDA means electronic design automation tools. So these things, you can verify, you can validate that, okay, our design or product or our system, whatever, functionally correct, right? Now I want to check it whether it will work fine at hardware level or not. And that platform is called basically emulation platform. So there are two types of platform. One is simulation framework, another one is emulation framework. Simulation related to basically software, emulation related to hardware. Software level realization is called simulation. Hardware level realization is called emulation. And this emulation platform, this emulation thing you can do with the help of FPGA, field programmable gate array development board is available. And through development board, you can validate whether your design or product will work fine at hardware level or not. Apart from this, scripting, Perl, Python, TCL, these scripting are required for automation purpose. And you are familiar with, most of them are familiar with Windows, right? Now, most of the EDA tools are compatible with the Linux or Red Hat, Scientific OS, Scientific Linux, CentOS, and so on. So you have to learn Linux. And apart from this, we know that nowadays it's the era of AI/ML. Almost all of you already heard about it. Irrespective of any particular department or domain, AI/ML nowadays applicable for everywhere. Application specific. You can apply AI/ML for mechanical, AI/ML for electrical, AI/ML for electronics application, or computer science is already there. So we can learn a couple of various architecture for basically which architecture is compatible or for AI/ML or suitable for AI/ML frameworks and so on. So these things, only these things you just prepare, and that's enough to enter into the domain of VLSI design. And all the resources are available everywhere, almost everywhere. You just focus on. Invest 6 to 8 months to learn all these things, and you will become a VLSI expert, including weekends. So let me tell you briefly. One is CMOS VLSI design concept. Then digital electronics, analog electronics, both for mixed signal. Computer architecture, knowledge of computer architecture is preferable. There are two types of hardware description language for VLSI, for VLSI chip design. One is VHDL, another Verilog. You go for Verilog because Verilog is most user friendly and most of the industry they prefer. This is one of the oldest languages. Now UVM and system Verilog, for those who are looking for, there are a lot of verticals up there. I'm going to discuss in the next slide. Okay, next slide. That is what are the options are there for VLSI engineers. Now verification engineer, if you want to become a verification engineer, then you have most of the jobs are related to verification engineers. More than 90% jobs are related to verification engineers. For verification engineers, you have to learn UVM, universal verification methodology, and as well as system Verilog. Now, if you are looking for software job in VLSI semiconductor industry, learn C, C++, Java, and so on. Now, whatever you have designed with the help of Verilog language, that is, you have validated with the help of software, that process is called functional verification. Now, if you want to realize in the form of hardware, that is called basically emulation framework, or with the help of FPGA development board, you can do it. Now, apart from this, you have to learn a couple of scripting for automation. Then in addition to that, you have to learn Linux. And these tools are basically, most of the tools are licensed version. Now you might have questions that if you don't have this kind of tools, then what we should do? So one thing I would like to highlight, those who are really interested to explore VLSI design, the Ministry of Information Technology, Electronics and Information Technology, they provide free access of EDA tools nowadays. What you have to do, you have to apply. There is a CTS website is there. If you need any kind of help, I will help you. You have to apply for EDA tools. They'll give you the n number of licenses. Now you can give hands-on demonstration to your students, and student will invest a lot of time, explore this tool whenever they will get free time. If you are not able to get the licenses, because these tools are very costly, academic purpose is very much less. Almost 10 user cadence tool. If you want to buy for academic purpose, academic bundle, you have to invest 10 lakhs or 12 to 15 lakhs. For synopsis, around 15 lakhs. And rest of the tools, again, same thing. So around to get these tools, you have to invest, initial investment would be approximately 30 to 40 lakhs. Maybe if you are having any funding issue, second option is you can send a request to MIT that we need the access of these tools. MIT will give you the access of this tool through CDAC Bangalore. Locally, you can install these tools, binaries, and CDAC Bangalore, you can invoke the licenses or from the CDAC Bangalore. And in this way, you can install, you can establish a VLSI lab in your institute. Apart from this, if you are not able to do this, then another option I'll tell you in a short while. With the help of open source platform, you can also design a VLSI chip. Okay, so now another skill set for testing and verification engineers, because most of the jobs are related to testing and verification engineers. So if you are interested in the domain of verification, then try to cover this following topics like fault modeling, logic simulation, ATPG, DFT, BEAST, MB, built-in self-test, memory built-in self-test, boundary scan chain. This book is available on, so soft copy is available on the Google. You can download it and you can go through this. A lot of materials are available, resources are available nowadays. So this is all about, these are the skill set required to become a VLSI engineers. So I'm not telling you have to learn everything. So maybe point 1 is important, 2 is important, 3, 4, and most of the things you have to. And if you're not interested in software, so you can no need to explore the software domain. But now the next generation, maybe if you have knowledge of software as well as hardware, industry will give more preference to you. So only software, only hardware knowledge will not be enough to survive in future. Now, types of VLSI engineers. So under design phase, logic engineer, static time analysis, physical design, standard cell engineers, then verification, DFT, IO, design engineers. These different types of engineers are there. If you want to become a ST engineers, means you have to validate the timing requirements and so on, or speed of your processor and so on. Then only focus on STA, that is enough. Now, if you want to develop, if you are very much expert in the domain of basically software coding and hardware coding and so on, software coding, so then you can go for this EDA tool development, electronic design automation, like Synopsys, Cadence tool companies are there. You can join over there. Development, methodology, application engineer, product engineer, validation engineers. You can join in a fab lab, post silicon validation engineer, test engineer, automated test equipment engineers. And apart from this, after PhD, so this is one domain. You can join after BTech, you can join after MTech, you can join after PhD and postdoc. So if you joined after MTech, maybe you can join in a R&D section, or after PhD you can join in a R&D section. So what you have to do, you have to think about new idea. You have to file a patent, and you may write a white paper for that. If you achieve a kind of breakthrough, something related to VLSI industry, VLSI technology. So these are the different types of or possible options for VLSI engineers. Now, Now let me tell you about VLSI design flow. So we have already covered why VLSI. Now what are the skills required for VLSI design? What are the companies are available? Now let's few minutes I will talk about VLSI design flow. In case of VLSI or semiconductor, the VLSI design flow, there are 3 types of, or typically 4 types of design flow. Four types of design flow. So first one is basically semi-custom design flow or ASIC design flow. Semi-custom design flow. Second one is full custom design flow. Third one is mixed signal IC design flow. And fourth one is programmable device VLSI design flow. Now let me tell you, semi-custom design flow is applicable for digital VLSI design. Semi-custom means basic components already you have designed with the help of full custom, and you have stored in the form of database. That database is called basically standard cell library. While you are using digital design, when like processor design, RISC-V processor and so on, then you can face those basic, you can map your logic with the basic cells, standard cells, and for the final hardware level implementation. So semi-custom is applicable for semi-custom. In some part you are designing, and remaining part you are using existing cells. Semi-custom, not you are doing everything. And this is applicable for digital IC design. In case of semi-custom, most of the steps are automated, apart from RTL coding, means coding part. Rest of the steps you can complete with the help of script file. The next is full custom, like any analog IC design or memory design or standard cells design. These are comes under basically, these come under basically full custom design. Mixed signal like ADC, analog to digital converter, or digital to analog converter, this comes under basically mixed signal design, VLSI design flow. Programmable device like logic array, gate array, FPGA, this, if you want to develop this kind of board, this comes under basically programmable design flow, VLSI design flow. Now you have to select that which domain you want to go. Semi-custom, full custom, or mixed signal. Programmable I am not discussing right now. Now let's talk about the semi-custom design flow. So VLSI, it's all about this flow or nothing else. One only thing is you have to learn this flow. One is front end, back end, and tape out phases, or physical design, physical verification, physical verifications. Okay, mainly these two, front end and back end. These two things are important. Under these two things, RTL coding, then logic synthesis, then partitioning. This comes under basically front end design steps. Content part. And back end, basically, back end means physical design part. Under physical design, floor planning, power planning, placement, clock tree synthesis, routing, and design for manufacturability. So you can work in the domain of front-end engineers, you can work in the domain of back-end engineers. So you have to select, you have to choose your path. And for each and activity, there's a different tools are available. From Cadence or Synopsys. So for to perform each and every activity, you have to explore different types of EDA tools, which is quite interesting. Okay. So basic steps is, I'm telling you one thing. You will have your target applications. Based on your target application, you have to define your specification. Based on your specification, you have to do RTL coding, register transfer level. RTL coding you can do with the help of VHDL or Verilog. Because there are two types of HDL languages. So once you do RTL coding with the help of Verilog, means you have implemented your logic like AND gate, for example, to input AND gate or to input NAND gate. Okay. So you have implemented with the help of Verilog. Now you need to verify whether your implementation or whether your module is functionally correct or not. That thing you can verify with the help of that process is called functional verification. Once your functional verification is over, then move forward for synthesis. Synthesis means you are converting your RTL code to your gate level or hardware level. This process is called synthesis. Once you have done synthesis, then move forward for physical design. And under physical design, couple of steps are there: floor planning, power planning, placement. Floor planning, like if you want to build a house, you will have you need a lot of planning, like which part would be dining room, living place, kitchen, restroom, and so on. Accordingly, you have to plan. Similarly, in case of chip design also, similarly in case of chip design, you must have this kind of plan. Okay, this side your analog IP, this side your digital IP, this side your mixed signal, this side your memory component, and under everything you are considering inside a single chip. And this chip is basically nothing but a system on chip. Means everything you are inserting onto a single chip, which will act as a system. It is called system on chip. Now floor planning, power planning, under physical design, floor planning, power planning, placement, then clock tree synthesis. You have to distribute the clock across your chip, then routing, then finally you will be able to generate the GDS2 file. This GDS2 file, you have to send it to the fab lab for final tape out. And this GDS2 file is nothing but a database or description of your design in the form of layers. Then fabrication lab only understand the layers. Accordingly, on the top of the silicon wafer, they will deposit each and every. So suppose this side is source, this side is drain. In between source and drain, channel will be formed after applying certain potential. Then silicon dioxide layer, then gate layer. So 3 terminals, then substrate, and so on. Accordingly, you can in this way you can prepare your NMOS and PMOS, connect them together. It will become a CMOS inverter or CMOS technology, right? So then finally you can test it out through the test facility. ATE, automatic test equipment. So there are three typical steps are there. You have to keep in mind. One is RTL coding and functional verification, first step. Second thing is synthesis. It's a process, conversion process from RTL code to your basically your soft code to your hard IP, hard code, or hardware level implementation. This conversion process is called synthesis, and third one is physical design. So all these 3 steps you have to learn. VLSI is all about these 3 steps in case of semi-custom design flow. And ASIC means application specific IC. So IC may be your analog IC, digital IC. If you are designing for particular application, that is called ASIC. It may be generic format form also. You can develop a generic product also. Means the same product can be utilized multiple applications. So you just learn these 3 broad steps. RTL coding, then synthesis, then PD. Digital VLSI, it's all about these 3 steps. Then apart from this, some small steps are there. What about the steps before the pre-synthesis? Pre-synthesis, some linting, CDC, XDC, X-propagation, RDC, these steps are there. It's a matter of hour. And post-synthesis, like equivalence check, then your timing analysis. Okay, if suppose you are going to develop a RISC-V processor and your target clock frequency is 3 gigahertz, okay, now you have to ensure that after the tape out, your processor should achieve 3 gigahertz speed. That thing you can ensure with the help of timing analysis. So most of the industry, they prefer static timing analysis because it is much faster than other types of timing analysis. So you have to, as I mentioned that if you are looking for digital VLSI design domain, then you learn these 3 tapes: RTL coding, then synthesis, then physical design. And rest of the steps are like silicon number insertion, seal ring, physical verification, and finally GDS2. Then bonding diagram means connection between core area to the packaging. This is called bonding diagram. And these are not the vital steps. Okay, you can learn within an hour. But 3 broad steps: RTL coding, synthesis, and PD. Digital VLSI, it's all about these 3 steps. And now, so previous one I talked about semi-custom. Now let's talk about full custom. Any digital design like processor, any digital circuits you can design. If you want to develop a chip in your lab, also available, a lot of ICs are available to perform the different digital experiments. So everything generally follow this process. Now for semi-custom, if you want to design an op-amp, if you want to design a amplifier or low noise amplifier or some other mixer or oscillator and so on, or LNA or PLL and so on. So for this kind of, or memory, SRAM, DRAM and so on. So for this kind of component, you have to design, you have to go another type of VLSI design flow. That is full custom design flow. What do you mean full custom over here? You are doing everything. So typical full custom means based on your target application, you have to define a block. Then after that, you have to design a schematic based on the transistors. Okay, suppose CMOS inverter, if you want to design, you need a PMOS as a pull-up network and NMOS as a pull-down network. Connect PMOS and NMOS input, get terminal together, give input, and observe the output from the drain terminal, and give the supply. VDD will be connected with the source terminal of PMOS, and ground will be connected to the source terminal of NMOS. Give 1, output will be 0, and then give 0, output will be 1. Based on PMOS and NMOS will be 1. If you want to design an inverter, then maybe you have to follow this kind of flow, like schematic. Then once you design a schematic, then netlist will be generated. Netlist means it's all about circuit informations. Then perform simulation, whether in case of, for example, in case of CMOS inverter, if you are giving input is 0, output is 1 or not, this needs to be verified. Then layout in the form of different layers. Okay, design a layout, then check the DRC, design rule checks, or perform the LVS, whether your schematic and whether your layout and schematic, so both they are equivalent or not, whether there is any mismatch or not. Now due to this low level implementation, you might have a lot of impact of a lot of parasitic components in the form of resistance and capacitance. Now you have to do some impact analysis, whether your parasitic components are basically affecting your characteristics of your device or not. that thing you can verify. You can, what we do, we extract the parasitic component, we add back to your circuit, and we perform the simulation. This process is called basically back annotation. And once you are satisfied with the functionality, everything, then move further for spec verification and block delivery. Means here also your GDS2 file will be generated, and send this GDS2 file to the fabrication lab for final tape out. So this flow, basically full custom flow, you have to keep in mind schematic design, layout design, then your back annotation. These 3 steps are there, major steps. These 3 major steps you have to follow. Like in case of digital, previous example, I talked about RTL design, synthesis, and PD. Here also your schematic design, your layout design, and back annotation. These 3 steps are involved. And finally, here also your GDS2 will be generated. Here also your GDS2 will be generated. Means final output file. This file you have to send it to the fab lab. Up to schematic design or netlist, you can call it here. You can call it front end, and layout to rest of the steps you can call it back end. Here also you can divide into two different categories. You can work in this schematic here as a front end engineer. You can work as a back end engineer. So these are the 2 typical flows are there in case of VLSI design. Only thing is you should learn these 2 flows. Now imagine how much time it will take to learn these 2 flows. 1 month, 2 months, 3 months. Then do certain hands-on with the help of EDA tools. If it is not available license version, then go for the free version. Those are openly available on the open source as an open source platform. Then already we have developed at NIT Durgapur, we have dedicated VLSI lab, SMDP supported, or Ministry of Information Technology and Electronics Information Technology. They have already supporting us. To what are the need, what are the objective to support us? We have to develop. We have got one project from Ministry. The name of the project is basically the scheme of this project is C2S, Chips to Startup. Under this umbrella, what we have to do? We have to generate 85,000 skilled manpower in the domain of VLSI design in the next 5 years down the line. That is our primary objective. We have to train our students, not only our students. If some students they want to explore VLSI design and they want to pursue intern over here, they're always welcome. So we have designed. This is the internal or final layout of a chip. Suppose memory design people we have done, and we have design part we have done over here. And we have sent it to the basically CDAC Bangalore. CDAC Bangalore, what they do, they validate it. Then whether our design as per the Fab Lab guidelines or not, because your design should be as per the Fab Lab or Fabrication Lab guidelines. Otherwise, they have mentioned their layer length is suppose 2 micron, and you have design consider during the layout 4 micron. Then they will not able to take out your design. So you have to design as per their guidelines. Then only they will be able to take out your design. So this type of final layout you can design over here. This is nothing but this is your core area. Core area means computation area. These are your input output pad. Means if you want to communicate your inside to outside world, these IO pads are required. A lot of VDD and ground and power rails are available to provide the supply. This is your actual real chip design. And then accordingly you have to design a bonding diagram, means which pins should connect to which means at after the packaging. Okay, this is the output. So you know this is a chip is coated with the black plastic and so on in the form of packaging. Okay, so under packaging there's a lot of leads are available. So these are the nothing but leads, golden leads. This connection you have to provide to the packaging companies, and they will do the packaging accordingly. Then we have developed a lot of, this is without packaging, buried chip, and with packaging. Recently we have received this chip, and 2 to 3 chips are already under tape out phase at SCH Fab Lab. And this is our project team along with our collaborator. This is testing we have done, and functionally after PCB we have developed, because we have inserted our chip top of the PCB board, and we have tested it with the, for testing we need lot of testing equipments. Like one of the major equipment is logic analyzer. You have to test it, okay, whether you, whatever you have designed, whether it is functionally correct or not. You give proper input and observe the output, whether you are getting your expected output or not after the tape out. Before tape out you are doing multiple times verification, and after the tape out the success will come when you see after the tape out what you are getting expected outcome. Okay, so we have tested our chip successfully and it is running fine. This is another 2 chips. One is fully digital basement modulator, another hardware accelerator based on CNN based hardware accelerator. We have developed these 2 chips, and these chips are under tape out phase at SCH. Now before performing before going for designing any VLSI chip, you must have proper plan. Plan means, suppose this side is top, bottom, left, right in your chip, right? Chip die area may be 2 millimeter by 2 millimeter or 3 millimeter by 3 millimeter. This is your chip die area. Okay, chip die area 2 millimeter by 2 millimeter. That means 4 millimeter square. Think about the sizes of the chip. And this is left side, outside, right side, top side, bottom side of the chip. Now you have to make plan. Suppose you might have a lot of input signal, lot of control signals. You have to, so if you want to give the input from left side, you want to observe the output from right side. You have, this plan you have to do, and you have to lot of rules or guidelines are available as per the fabrication lab setup. So they will give you certain space you have to maintain, or speech you have to maintain. And this thing, only thing is you have to maintain certain speech or space, and with a particular layer, and rest of the things are simple. So you must have proper chip planning. This is your core area. These are your power rails, VDD and ground. This is your input output pins. Maybe 50 pins, 60 pins, 80 pins, 100 pins are required for your chip. Accordingly, you have to place. The simulation and emulation platform, if you, I'm assume that you don't have any access of licensed EDA tools. Okay, that time what you do? You can do from your hostel room, from your office, wherever you are. So there are open source platform like iVerilog, EDA Playground for functional verification you do. Then there is a Qflow is kind of tool chain for each and every activity like synthesis, layout, then physical design. For everything, all the tools together, they have prepared one single platform that is called Qflow. So with the help of Qflow, you can design RTL to GDS2 file flow. You can complete. I'll show you one small video or small demo I want to give you in a short while. So these are simulation platforms. And emulation, already I told you, you need a FPGA board to perform whether you, whatever you have done, whether your logic is fine at hardware level or not, that needs to be verified. And for that, you need a emulation framework or emulation platforms. Now, Google, they provide basically open load or open lane platforms. Open load or open lane platform. What it is basically, suppose you thought about a new idea. You want to implement it in the form of chip, VLSI chip. But you don't have any resources. Because if you want to tape out a single chip through any fab lab, you have to invest 4 to 5 lakhs. But you don't have that much money. Now what you can do, you can design your chip with the help of open source EDA tools. This kind of chip. What you can do, you can design a VLSI chip with the help of open source EDA tools. Now send it to the open lane platform, which is maintained by Google. And Google will tape out your chip free of cost. And they will send it to your address. Then prepare your PCB board and so on and test your chip. Some basic test component also they provide. You have to give minimum amount of money like $10, $15 and so on. So this kind of platforms is also available. So only thing is required, that is your motivation towards VLSI design. Only thing is required. I'm sure that I'm accepting that you don't have access of licensed version or cutting edge technology based EDA tools, but you will have access of these open source platforms from your laptop or desktop, whatever. With the help of these platforms, you can design a RISC-V chip also, your processor, and you can observe you can perform different types of arithmetic and logical operations. You can perform different types of arithmetic and logical operations. Once you developed your design, you have generated your GDS2 file, then send it to the open lane or open load platforms through Popper channel. They will tape out your chip free of cost and they will send it to your address. If you are really motivated to learn VLSI, then go for this one. If you don't have any other access or facility. So before blaming anyone, you can do this thing standalone. So now, apart from this, okay, this is one important link I'm providing you to learn. If you want to learn scripting, then UVM and system Verilog, then Verilog, and lot of stuffs. Then this dolas.com website is available. You can learn. Maybe some workshop is always running over there. You have to pay some amount for the registration and so on. So this is another platform. A lot of industry personnel also they use this platform. So with the help of this Raven RISC-V microprocessor from eFabless, means you can, so digital code was placed, routed by Qflow, verified with the Vesta, the top level assembly was done with the Magic and verified with the NetGen. Means this Qflow, Vesta, Magic, NetGen, all are open source EDA tools. Open source EDA tools. So you can design this type of microprocessor, this type of processor with the help of open source EDA tools. No need to take any help from anyone. No need to invest anything. Only investment is your time. You can do you can achieve the same thing, whatever we can achieve with the help of license version tool. Only thing you have to compromise, whatever free version technology nodes are available, like Sky 130, with the help of those technology node, you have to tape out your product. But it's fine, we can accept it. So earlier phases also, we have developed a lot of ICs along with IIT Kharagpur and so on. So VLSI department at NIT Durgapur, it is in proper track. Every year we send whatever MTech students those who are doing MTech over here, we send it to the Intel or some other companies. Intel, they take generally more than 80 to 90% student every year, and they absorb it, and their salary is very competitive, more than 30 lakh, 40 lakh, 50 lakh, and so on. Some emerging technologies like Farewell to FinFET. So now we are moving down to FinFET, planar MOSFET to the basically FinFET to nanosheet transistor and FOX transistor, gate all around. Now industry, they are exploring this thing, most of the cases. Ongoing or upcoming technology like in-memory computation or near-memory computations. It is part of non-von Neumann architecture. Neuromorphic or hyperdimensional computing for high-performance computing, hardware for AI/ML or DL or framework, hardware level realization, emerging interconnect architecture. For this type of realization, you have to perform high-level synthesis or ASIC level implementation. For next generation SoC, 3D technology, quantum computing, hardware security. These are the ongoing upcoming technologies you can explore if you really want to pursue research in future. These are the couple of important resources like International Technology Roadmap of Semiconductor. It will give you some idea about what's going on in the present industry or semiconductor. What will happen in the next 5 years down the line? Although it is quite old report. Now best processor for designers, computer architecture. There is a pioneer, one of the pioneer academician, that is he spent a lot of he has a lot of industry experience. Professor Onu Mutlu. He is from ETH Zurich. Okay, you can follow his lecture series to learn the basic computer architecture. Why India is building a mega semiconductor facility? It was quite old news, already you know. And future of semiconductor industry, if you want to know about the future. And there's a 5 critical steps, pipeline steps. Already I told you in detail. 5 critical steps are like introduction and foundation. You must have. Second one is synthesis. Third one is floor planning and placement. Fourth one is block tree synthesis and physical verification and signing off. So VLSI, it's all about these 5 steps. These 5 steps. Introduction and foundation, synthesis means this RTL coding and everything, architecture definition, floor planning, placement, clock tree synthesis, physical verification and synthesis, and so on. And these steps are already I told you. No, I'm not going to discuss about it in detail. Okay, if you have any question, I'll take you. Before that, I just want to show you one thing. This type of platforms, let me check. Okay. This type of platforms are available. You have to top up the virtual machine. If you have Windows-based system, top up the virtual machine, top of the Windows, you can install the Oracle VirtualBox. And under Oracle VirtualBox, you have to install the Ubuntu. And to explore the open source EDA platforms to design a VLSI chip, then go for start option. Okay, start option, and just a minute, it may take a few seconds. Yes. Just a minute, please. You have to do login, resonance @123. So this is simple. Actually, if you have suppose Windows system, then what you can do, you can install Oracle Virtual Box or Virtual Machine in your desktop. Okay, and top of the Oracle Virtual Machine, you have to install the Ubuntu, and top of this Ubuntu, you can install all the EDA tools, open source EDA tools. Like I can show you one EDA tools over here. You can have maybe, I assume that if I want to give you full-fledged demo, then again it will take half an hour. So better to I just want to show you one basic thing to motivate you, or maybe towards the open source EDA platforms also. So suppose you have done functional verification with the help of iVerilog or EDA Playground EDA tools. Now you want to complete the rest of the steps, starting from synthesis and so on up to GDS2. Then you just write Qflow and GUI. Okay, Qflow and GUI, and your Qflow tool will open automatically. It is free of cost. There is technology note, either 180, 350 or 500. It is quite old, but for learning purpose it's fine. Industry also accept if you know, if you tell them, if suppose VLSI company will visit your campus. Okay, if you inform them, we don't have license of Cadence and Synopsys EDA tools, but we have explored VLSI design with the help of this type of open source EDA platforms, they'll be more than happy. Okay, so now there's you can see from left side, synthesis, placement, static analysis, routing, post-route, STA, migration, then DRC, LBS, GDS cleanup. Okay, then what you have to do, you just select the technology node, particular technology node. You have to give your, basically, you have to select your source file, your design file. You can select your design file, like, yes. For example, let's do with this one, counter.v. Okay, you just select on it and click on run. After running, you will get all the steps will be executed simultaneously. Okay, if some problem arises, it will stop there only. If you run like this type of options, then a couple of things will parallel automatically. Okay, couple of things, routing, placement, this whole flow. Okay, then if I'm having some issue, then might be there's an issue in case of migration. I have to check it, the report and so on, and then I have to debug it. Then finally GDS2 will be generated. Okay, in this way, you can explore this tool, and you will see the final basically final GDS2 file, and this GDS2 file GDS2 file will be generated over here. Suppose layout file will be generated under here, your log file will be generated under here, and GDS file will be generated here once it will complete in successfully done all the pages. And you can extract the GDS2 file and send it to the Fab Lab for final tape out. And your open lane or open loan, which is provided by the Google, mentored by Google, they'll tape out your chip and will send it to the for your testing and so on. So this is all about regarding my today's session. Now I would like to happy to take your questions if you have. Thank you.
So thank you very much, Dr. Mandal, for this wonderful, encouraging and motivating session on design of VLSI with open source resources informations. Your way of explanation has made the participant to learn the concept in easier way, and we are truly privileged to have benefited from your wisdom and knowledge in the domain of VLSI design. So once again, we are thankful to our alumni, Dr. Mandal, for giving us your valuable time for the benefit of our participants, and we request you to come down to your graduate institute BCET when you are free to motivate our present students physically. And now, Dr. Mandal, I would like to inform you that our respected director, sir, Dr. A.C. Ganguly, was the part of your session, and
Okay.
he wants to compliment your performance and hard work. So, Director sir, please.
Sure, sure.
Hello.
Yes, sir, you are audible.
Yeah. So, Dr. Hemanta Kumar Mondal, fantastic presentation. Where are you? I'm not able to see you. Hello, Hemanta.
Yes, sir. I'm available.
Yeah.
Fantastic presentation. So, thank you very much. And what I find out is that from NIT we are taking a very important step in orienting the students in VLSI. So
Yes.
that is a fantastic. We are very much interested. Particularly our electronics and communication students are very few, but I'd like to have interdisciplinary approach.
Yes, sir.
Right. So
Yes.
please help. So interaction will go on. I like our department, TC department, and other departments to contact you. Our student will be interested to go there as an intern, like other colleges also. You have to be so many people are required in VLSI, design and manufacturing.
Yes, sir.
So actually, you are doing a great job. We are proud of you, my dear friend. So we're so happy, and you'll be inspiration to our students, faculty, everybody. Okay, go ahead with your job. Thank you very much, and like to see you once again.
Sure.
And come in the college and inspire the student. That is what is required. In your stages, we have talked about that how students are only for jobs. Students must go, like you have said. They must appear for GATE, and some of the students, I am not taking all, some of the students must get oriented. What you have said, they should appear very seriously for GATE and go to higher studies in VLSI in some of the good colleges, and then go for jobs or statewide design or manufacturing. Fantastic.
Thank you, sir.
Very much.
Thank you, sir, for your compliments.
Thank you.
Now, from the participants, if anybody has any query, please feel free to clear your queries from Dr. Mondal. So, anybody, please come forward.
Someone raised on hand.
Okay. Yes.
Suroy. Yes.
Sir, I have a question, sir. Sir, what is the role of advanced semiconductor manufacturing nodes like 5 nm and 3 nm in VLSI development?
So yes, so actually the basic reason is whenever you are moving from one technology node to another technology node, that means if you get certain benefits in the form of power, performance, and cost. Okay, and that thing we can ensure with the help of PP analysis. So company, suppose it's if you able to reduce the power consumption, as a consequence, we'll able to enhance the battery life. Now today's era is kind of EV era. Okay, so battery life is important. So in that case, power, if you as much as we can reduce the power consumption, so with the help of some emerging technology or emerging power saving schemes, so battery life will be enhanced. Okay, so one of the reason is to move lower nanometer, ultra lower nanometer technology node is in terms of if we get the power benefits, if we get the performance benefit in terms of performance. Suppose if our target performance is 5 gigahertz, we want to run our processor, so we can move further, we can scale down our present technology node to certain technology node, targeted technology node. So three things are important. One is power, second one is performance, and third one is cost.
Okay, thank you.
Thank you.
Anybody, please? Anybody else? So, thank you, Dr. Mondal.
Thank you.
It was nice.
Thank you.
And hope we'll again organize such FDPs in future.
Sure,
Specifically, we are planning for auto FDP in the next the middle of this year.
Okay.
So we hope will support us in like this.
Sure,
so thank you very much. And dear participants, I request you to stay tuned after the lunch with the second session at 3 p.m. on how porous materials are powering smart engineering solutions by Dr. Vivekananda Sharma from Institute of Porous Material, Paris. So thank you all. So by this, we conclude the day 4 first session of this faculty development program. Thank you.
Okay, thank you.